Swayam Prabha. Digital India. Educated India.
Good morning everybody. Today we will be concentrating on design issues of vacuum chamber, which is a very important topic as a part of module 4 dealing with chambers, materials, components and couplings. Okay. The concepts that are going to be covered in this lecture are some basic introduction to the design issues that we normally encounter while making a big vacuum chamber for different applications. And the most important parameter of a vacuum chamber is the thickness with which you are going to make the chamber, because it is the material's thickness that matters a lot. If you do not design properly, you end up in spending a lot of money in oversized vacuum chamber materials, and if you make a mistake of undersizing, you end up in accidents. So both ways it is very dangerous. So a intelligent engineer has to do good thickness calculations before purchasing the materials with which you are going to make a chamber using suitable fabrication issues like brazing, welding, fitting, etc., etc. Okay, so that thickness calculation depends on ASME codes which are internationally accepted, and we will take up some examples and try to make some calculations so that the idea of finalizing a chamber design with respect to thickness, you get some ideas, particularly those people who have never handled any big chambers. You will get some idea how to proceed further. But recently there are a lot more things are happening in these calculations. In the sense, computers are helping us a lot with very powerful softwares in console and ANSYS, where using FEM methods, we not only can calculate the thickness, we can also figure out the stress concentration zones at various locations. These are very important when you are making very large chambers like International Thermonuclear Experimental Reactor ITR, where you are going to get future energy. Almost we are simulating sun using nuclear fusion, or particle accelerators like LHC, a very large ring of 10 to 7 kilometers. These are all very large chambers. So if you make a mistake in thickness, you will end up in either accident or oversized material with a lot of cost. Okay. Then when it comes to metallurgical furnaces, the chambers have to be designed not only with respect to structural strength but also the temperatures. Okay. And sometimes you have to do thermomechanical aspects into consideration when you are going for design aspects, not just only the thickness. Similarly, the surface finish inside is going to be very important. The apparent area that we see with our naked eye inside surfaces which are actually exposed to vacuum are much less compared to the actual area, because unless you polish it very nicely, just 2 pi r h is not the area of a cylindrical shell. It may be much more because there is some 10 micron bad finish. So material, if it is not properly polished, the molecules, particularly in molecular flow situation and ultra high vacuum conditions, they are exposed to a very large surface area because they can go to the internal micro cavities because of roughness. So that is also very important in chamber manufacturing. So thickness calculation and some thermal issues, and finally the surface finish. All these things should be decided before you take up the fabrication of a vacuum chamber. After covering these concepts, we will try to give conclusions with some hints to the engineer what he should look into with regard to the design of vacuum chamber. For your information, the vacuum chamber is the main component because other components are commercially available: valves, couplings, gauges, plumbing work. These are all standard. Very good materials are available, very good components are available. What is to be done by the engineer in a particular application is mostly chamber design. That's why we are giving a lot of importance to the design of vacuum chambers. When you look at this figure, you can get a feel. Any metallic vessel, it can withstand 4 atmospheres of pressure, internal pressure, outside atmosphere. As per ASME codes, you can design also. Roughly, it can withstand same vessel under similar thickness and similar length and diameter ratios, etc. It may not withstand even 1 atmospheric external pressure. That means under vacuum, outside 1 atmosphere, inside it can be considered as 0 because not 1 is same as 0 with respect to mechanical force considerations. Even then it may collapse, and that's what you are seeing in this figure. This is a reality where a very long metallic chamber without vacuum, and it is connected to a vacuum, and as soon as the vacuum level goes to 1 tar or 10 tar, immediately the entire chamber collapsed because the thickness was not properly designed. And if it collapses 10 tar, it may not collapse at 500 tar because P2 minus P1 into area is the net force. And this is an implosion, it is not explosion. For high pressure vessels, it is the ultimate tensile stress, hoop stress, those things we will be covering. For the vacuum vessel thickness calculations, we will be going to ASME code section 8, where external pressure vessel equations are used, and inside pressure is taken as almost 0 and external pressure is taken as 1 atmosphere. And here I want to give you one hint. If a chamber is tested up to 1 tar or 1 millibar, it will anyway withstand 10 power minus 10 millibar from mechanical point of view, not for getting a very good vacuum or leak rate or chemical problems. That is a different thing. Mechanical compatibility, where the force comes into picture, the implosion takes place. For such issues, if a chamber is tested up to 1 millibar, you don't have to test it up to 10 power minus 10 millibar because of simple relationship. 1000 millibar, that is 1 atmosphere absolute, minus 1 millibar is same as 1000 millibar minus 10 power minus 10 millibar of a UHV unit. So with respect to mechanical force or implosion or thickness calculation, it is good enough if you test the chamber up to 1 millibar. And the collapse is taking place in a vacuum chamber from a different phenomena. It is not like tensile stresses or hoop stresses in a cylindrical vessel. Here it is a different phenomena known as elastic instability. Well, there is a lot of research for this study. You can go through literature to understand what is elastic instability, etc. But today we are going to discuss briefly only the thickness calculations. So, the thickness has to be calculated from external pressure conditions using ASME section 8 code. These calculations for a particular vessel we are giving, but these are applicable to any vessel. You have to take necessary L and D and thickness and guess values and try to put them in the equations, get output, check whether it is okay or not. In a reiterative calculations you have to do. You can do it manually, and if materially changed, that material property also will come into picture. Today, of course, there are good softwares available also. We will see all these aspects in the next slide. Okay, let us take a particular chamber. From geometry point of view, we can consider it as a cylindrical shell, and either side there will be either hemispherical or elliptical type of heads. Okay. That we are not going to see right now because there are equations for that. The main calculation which we have to concentrate is the central shell, which is the biggest component. What will be its thickness? So, let us take an example now. Before that, we have to decide which material we are going to talk. Here I am going to take SS304, which is very popular in vacuum technology. You can use mild steel, you can use other materials, aluminum, etc. in very specialized situations, or whenever your budget is not allowing you to purchase a very high quality stainless steel. But when it comes to 10 power minus 10 torr, budget is not the problem. Reliability is very important because the pumps and other components are very costly. So, the material with which you are making chamber also should be quite costly without any micro cracks. Very good finishing has to be done, sufficient thickness, if necessary external stiffeners have to be added, all that goes into that. Very detailed design has to be done for ultra high vacuum chambers. In our particular present case, we have taken SS304, length we have taken it as 1000 millimeter, that means 1 meter, and the diameter we took it as 500 millimeter, 50 centimeters. It's a typical of many chambers that we see in laboratory atmosphere or even little bit of small scale industries. But when it goes to very large scale industries, the chambers may be of the order of this building size, like space simulation chambers or particle accelerators. Accordingly, these L and D will vary in the calculations. In our present case, L is 1000 millibar, D naught is Di, that is 500 millibar, plus the assumed thickness, which we have to finalize now. Let us guess a thickness of 2.5 millimeter to start with. This is the starting point. So, what will be outer dia? 500 millimeter plus 2.5 plus 2.5, it will be 505 millimeter, with which we will make dimensionless parameters D naught by T and L by D naught. D naught by T is outer dia by thickness, guess the thickness, and L by D naught is L by D ratio of that chamber. In our present case, it will be 505 by 2.5, that will go up to 202. L by D naught is 1.98, roughly 2. Since we are taking D naught, it is coming out as 1.98. And this chamber is exposed to vacuum inside and outside, of course, natural atmosphere 1 bar. So, the pressure differential will be 14.7 psa or 1 bar. But we have to give some safety. So, the design pressure for which we are calculating thickness will be, let us say 1.3, which is a good enough safety, into 14.7. So, roughly 19 psa, let us say 20 psa. So, for that external pressure or pressure difference, external pressure is same as pressure difference for vacuum chamber because inside pressure is taken as 0 almost. If you are at 0.1 or 0.01 with respect to external pressure of 1000 millibar, it hardly matters. And if you take a particular element of this surface, one side atmosphere, other side vacuum. It may be 10 power minus 3 millibar or minus 10 millibar. And force is going to be constant once you cross 1 millibar, because pressure difference is responsible for force. And to get a feel of it, on every square centimeter, if 1 kg stone is sitting, that much force you can expect. Of course, while finalizing the thickness, you have to go through rigorous procedure of calculations. Otherwise, either you will end up in accident or unnecessary usage of costly material. Okay. So, with these input parameters, we have two charts. Don't get scared by these complicated charts. They are very simple charts. One is a chart dealing with dimensions. The other is dealing with the materials and temperatures. So, very briefly to a layman, I can say from the dimensions or dimensionless parameters, you go to chart A. That means in our case d naught by t, L by d naught. So, these two parameters you can use it here, and you have got different d naught by t curves here, 1, 2 varieties of curves, for which you have to take for different L by d naught things and calculate a factor known as A factor. Don't get into details of the ASME code. We have to get a dimensionless factor A depending on our L by d naught on various d naught by t curves. That is all the first curve, and these are available in ASME code. It is also available in Wikipedia. You can take from there. This is purely geometry related chart. So, thickness calculation starts from geometry. 3 parameters. One is thickness, that is guessed thickness, which we want to finalize, and d naught, which is the outer diameter, and length for a cylindrical shell. We will see for complicated shapes how to do later. Once you get the A factor, now comes to material properties, whether it is a stainless steel or an aluminum or mild steel or a plastic, that you have to see. So, there is another factor called B factor, which is plotted as a function of factor A obtained from the first chart. Once you get A factor from the first chart, all that we need to do is use that and take the curves for particular material with which you are making the chamber. In our case, it is SS304, and room temperature. So, you go to that room temperature curve of SS304 chart and go to that particular factor A, which you have calculated from geometry factors here. So, you have started from L by d, d naught by t. These are the two parameters which is very easy for you to finalize, and a guessed thickness from your experience. From there, go to these curves, find out the A factor. Use that A factor and finalize the temperatures to which the vessel is subjected to and the material with which the chamber is made. Then go to the second chart and get another parameter called B parameter. Once you get B parameter, now it is a child's game. So, the allowed P allowed external pressure difference, okay, or just only pressure, because anyway it is vacuum inside, pressure difference is same as absolute pressure. So, that is nothing but 4 times the parameter that we got B divided by 3 times the d naught by t, which we already know. And if that value given in the units of PSI, if it is more than the safe value, that is 16.1 PSI, we got it in the for any vessel, for vacuum vessel, 16.5 type of PSI is the safe pressure, or even 1.3, 19.11 for example. How much safety you want to take, it is up to you. If you take 1.3, it is 19.11. If you take 1.2, it is different. Roughly 1.3 is a safe value to take. So, this final thickness that we are going to calculate 22.45, if it is more than 19.11, well, I have written 16.1 because earlier we used to take safety factor of 1.1 etc. But 1.3 nowadays is the practice. So, it should be written as 19.11. Okay. So, 22.45 PSA obtained from all these calculations is more than 16.1. So, it is safe. Okay. With this safety, now you purchase the material. You don't unnecessarily purchase very thick, don't purchase less than this. Once you take up this decision, but if your boss says, no, I want and save more money, you make it not 2.5 mm, you make it 1.5 mm, so that I will save crores of rupees in the large chamber. Then how to do? You can add some stiffeners outside to this vessel, cylindrical vessel. If you add stiffeners, then you look at this left figure. The effective length is not the total length, effective length will be the length between two stiffeners. So, naturally, L for the design point of view is not the real length, it will be that much length. So, accordingly, the thickness will come out to be little less, because bending moments are less now, because it is held tight by stiffeners instead of a distant end couplings or end welded joints. There are stiffeners in between which are welded, of course. So, mechanical engineers know very well these type of things. That way, with stiffeners, the effective length will come out to be less and thickness can be little less. For small vessels, we don't do that. For very large scale vessels, for example, this is a cryogenic storage vessel for liquid oxygen, liquid nitrogen type thing in remote areas. So, it is a double walled vacuum vessel. For a cryogenic double walled vacuum vessel, outer chamber is a vacuum chamber and inner chamber is a little bit of pressurized chamber, because annular space is vacuum. So, annular space is the external pressure for the internal wall. So, double walled vessels have to be designed, one for external pressure, one for internal pressure. Outer vessel is nothing but our vacuum chamber. Then you will have to also take care, once thicknesses are finalized, very good polishing practices you should have, so that inner surface is properly polished, so that surface area approaches the apparent surface area, approaches the actual area. So, the degassing area, outgassing area will be less, it will be less load on the chamber. This we will see when we discuss outgassing issues, etc. They are not only for chamber, even for manipulators, everywhere, because degassing is a big issue, outgassing. We will be covering again and again, not only in chamber manufacturing, component manufacturing, even the processes, etc. So, when you do very good degassing, mechanical structural design is over, then inside finally it will look like that, optical finish. Then only you can get large scale ultra high vacuum chambers for very specialized applications. Then you will take care of end plates, whether it is hemispherical or a door type thing with necessary gaskets. That and all we have seen in the last class, gasket materials, clamps, etc. So, a chamber, vessel, these are all you can change these words. Sometimes you call chamber, sometimes you call vessel, shell, etc. And sometimes in metallurgical furnaces, this entire chamber will be in another chamber where water circulation will be there, like a heat exchanger, shell. That time, the hydrostatic pressure, if there is any pressure, that has to be taken into account also, in addition to the atmospheric pressure. Well, the story gets complicated as the pressure differences are increasing. And if the same chamber on earth, it has got a pressure difference, but if it goes to the space, outside also vacuum, inside also vacuum, then thickness can be very thin. But we cannot afford to do that, because to start with, the space shuttle has to go at atmospheric pressure. So, the design things come into picture. Once it is designed for a ground station, it is anyway safe, it goes into the space, because outer is also vacuum. Nowadays, very good softwares are available using console or ANSYS with finite element methods. Same vacuum chamber with stiffeners, for example, cylindrical shells. You have to make some meshing to make finite elements. This is a standard exercise done in structural design as well as CFD. Everywhere you do this. Nowadays, we don't have to explain engineering students on this because it is a magic box. The powerful software will take care. All that we need to do is we have to mesh the surfaces. That is where the beauty lies, how best you can do. And in very complicated areas, there are crucial areas, you have to decrease the mesh size so that accuracy of your calculation will be more and more. All that is done. Finally, what will you get? We will get parameters such as effective displacements in micron level or stress concentration zones. All that you can get it very easily. And if there are one stiffener, two stiffeners. So today students may not do this classical design using ASME codes because these are all already buried in the software. All that you need to do is mesh it. And near windows there will be additional safety because there are welded joints. There might have been some corrosion, weld efficiencies will come into picture. So you can do varieties of things. You have to give a modeling, then material definition, mechanical loads, boundary conditions, and finally mesh it. That's all. Then you give it to the boss computer and run it, FEM software. There are very user-friendly softwares even for a layman in console, etc., multiphysics, and just get all the output. But be careful to interpret the output, and if you are not careful, you may be making a mistake, and if a very smart employee suddenly get into trouble, particularly while dealing with mechanical structures, if he has made any mistake in boundary conditions or meshing or initial input parameters. And when you connect a vacuum pump, suddenly it may implode. So instead of impressing the boss, you may lose your job. One should be very careful when you are using computerized models for thickness calculations. But they are very user friendly. You can cross test it also with your numerical methods using ASME codes. So today many people are working on varieties of softwares. The beauty for this is you can add thermal field to the mechanical field because various temperatures, instantly you can put that as a parameter, as a boundary condition. And shape need not be like this. Shape can be complicated shape. Little later when we look at the applications in ITR or nuclear particle accelerators or space simulation, we will see how complicated shapes are there. If you go to the journal Vacuum or Vacuum Science and Technology, quite often you will find lots of papers with complicated vacuum chambers, etc. And stress calculations are done. You will get varieties of publications. They are very important publications. Okay. So the story goes endless depending on chambers, style, chamber geometry. You have to be very careful in mechanical designs. Mechanical design is not only thickness calculation, though we have highlighted it. Finally, there are other things like concentration zones, welding joints, etc. You should have a mechanical engineering knowledge and programming knowledge also, and materials knowledge, metallurgical knowledge. All these things are important, and of course vacuum knowledge. Then only you can be a very good vacuum technologist when you apply vacuum chambers for various applications. So to conclude, thickness calculations play a very important role from structural design point of view in vacuum chambers. And it is to be noted here, for testing purpose, if the chamber is tested up to 1 torr or 1 millibar, it will anyway withstand 10 power minus 10 millibar with respect to mechanical strength. Just because it withstands, it may not be a ultra high vacuum compatible chambers if it is a dirty or if it is not polished properly, and if it has got water inside, then you will get only 10 power minus 2 torr. even though structurally it is very good, even if it is leak tight. So leak is another problem which is also related to chamber. Outgassing is related to chamber. So chamber design is not only mechanical design, outgassing design, welding efficiencies and window materials, flanges, couplings, many things are there connected to the chamber. So it has to be dealt as a whole, as a system, but chamber is of course the main thing. That's why we are today discussing the chamber design. Then with respect to degassing or leak, rigorous testings have to be done after mechanical implosion is taken care. But if it implodes, then we need not do anything because it is no more a chamber, it is a junk. Okay. So fabrication follows, because fabrication of very large scale vacuum chambers is going to be very expensive. Material as well as fabrication. You cannot do any welding that you like. In the next class, we will see the fabrication procedures after finalizing materials, components and chambers. The first 3 lectures we have completed. So, in the next lecture, we will be doing fabrication issues. Based on these lectures and towards the end in 5th lecture of this module, we will be giving you some ideas of testing and quality control of vacuum chambers. So, friends, today we have seen more or less the chamber design aspects from mechanical engineering point of view, which is very important for vacuum technology. Thank you very much.